Okay, 1 second, please. Hi, I'm Neil, and now I will just check that you can see me and hear me. 1 second, and then we will begin.
Chinese open source may have
Okay, so you can hear me. So again, hi everybody. I'm Neil, and today we are doing my invention, VR2. I call it virtual because it's novel to help blind people. And Boxels. Boxels is blind voxels. Okay, voxels is like there is pixels, so in 2D. So voxels is in 3D, and Boxels is 3D but for blind people. Okay, so I will take the pen or the marker and let's write this. Okay, this is virtual reality for blind people. Okay, just lift the arm again. Okay, so when I say VR, it's virtual reality. Okay, like you have a headset and you put it on and you see another reality. But for blind people, it should be different because they cannot see. Okay. So I'm reading fast because we have 9 pages. It's a lot, so I will read fast. Today I invented a new invention, which I call VR2, read virtual, or Boxels, like blind voxels. And it is like virtual reality for blind people. This gives blind people complete immersive experience only through a combination of touch, movement, and sound, without vision. This does not use VR headset, like I showed you, or glasses, or haptic gloves, etc. Like Monty Python, and now for something completely different. Okay, so it's like the movie. It's basically 2 different inventions which do not combine. One is for large-scale seeing, and one is for small-scale seeing, both for blind. Both inventions are based on office toys. One is based on pin art, okay, so 2 office toys. Office toys is like you have like a Newton cradle that you have this in your office, and there is like this. I don't know how to draw it in 3D, but you know you have like okay, so this is Newton cradle, and when you take one of them to here and you let it go, then it goes to here and it comes back and it goes here. So it's not practical things, but now we will make it practical. So not this one, but we are using two different office toys. I don't know why my writing is so ugly. I have two inventions, and each one is about a different toy. One is about pin art. And one is about, the other is about kinetic sand. Okay, so if you don't know what this is like you have a board of many pins like nails, okay? Not nails like nail on the wall. So many of them in lines and many lines. And then when you put your hand into it, so it's like it's not painful, it's just pushing the pins and you see the shape of your hand, like from nails. Or if you put your face, you see the shape of your face. Whatever you put there, you see nails coming at you, like pins. Pins. Okay, but not sharp. Like, okay. And the kinetic sand is like magic sand. Okay. It's like they bake it with something and mix wax or something. It's just repellent of water. So it's not mixing in water, and like you can put your hand, you can put it on the surface of the water, it stays floating. When you put your hand into the water through the sand is like a glove, making like wrapping your hand with the sand and protecting your hand from the water. You do not get wet. Okay, so this is like it's magic. Okay, so we use both of these, but not in the same invention. One is for one invention, the other is for another invention. They are both about making blind people see, not see, but feel, enjoy virtual reality. Okay, so let's see how. Okay, but to understand how it works, I will first explain many unconnected simple building blocks that you know from everyday life. Please bear with me because later I will explain how to combine these simple concepts together in a new way, which makes this possible. The invention. Okay, building block 1, pin out. Okay, if you want to see it in Wikipedia, it's called pin out. There is an article in Wikipedia. Like Wikipedia says, pin out, also known as pin screen, okay, pin out or pin screen, is an executive toy, okay, like office toys or executive toys. Like for people who are bored. They put it on the desk and they play instead of working. Okay, so it's executive toy. It consists of a boxed surface made of crowded array of pins that are free to slide in and out independently in a screen to create a three-dimensional relief. Okay, like you have imagine this is like 3D and you have many pins. Okay, and like if you press against them, then from the other side they stick from the other side. Okay, wherever you press, like, and if you see it from the front, then you will see, for example, if you put your face, you will see like the shape of your face. Of course, you will not see colors or something, and you cannot see like the inside of your eyes, but you will poke out your eyes. You should close your eyes. But let's say you put your hand, then you will see the shape of your hand. Okay, like you put your hand, you will see your hand. Okay. So if you don't know, just Google and you will see. Okay, so in the original pin out, each pin was moved by hand and it was reset to flat surface again by gravity. You flip it so they all fall. Or if you make it lie down, then all the nails become the same level. Then you do not see anymore your face or your hand. It's like new. In our system, each one is controlled by the same electrical circuit. Here is how Google AI explains. You can skip it, I just show that it's doable. Okay, so now I'm reading a part like very technical from Google when I asked like how can I control electromagnets, many electromagnets from one circuit, and he told to activate different electromagnets independently, you can use a multiplexing circuit with a microcontroller like an Arduino and relays or MOSFETs. I will write it, but I don't understand it also, but it's like just a technical thing that you should do. It's like AI can help you do it. Someone who knows electronics can help you do it. It's like, it's doable. It's not, this is not the hard part. So I will just erase everything and write. to activate different electromagnets. Independently, you can use okay, and here they tell you what you use: multiplexing circuit, with a microcontroller like an Arduino. And relays or MOSFETs. I don't even know what it is, but it's something in electronics. Okay. Like MOSFET is the word, and MOSFETs is like if you have when lower. Okay. I think relay, don't like, be angry if I'm mistaken. I think relay is when you have a small circuit with low voltage and you want to make it control another circuit with high voltage, I think. But it doesn't matter, like this is from Google and it's like 99% right. And anyway, you can do this, it's possible to control a few, like even many electromagnets with a circuit, electronic circuit. Okay. Handle the high current switching for each individual magnet. One key components you need: power source, a robust DC direct current, like battery, power supply, like or like from the wall socket but with transformer to DC, like a 12 volt or 24 volt battery rated to handle the total current draw of all electromagnets that will be active simultaneously, microcontroller, an Arduino or Raspberry Pi Pico. Okay, so it's either Arduino or Pico. To send the activation signals. Okay, they give like the logic. Switching modules for high power or AC coils. AC is like alternating current, like from the wall socket. Use logic level MOSFETs, e.g., like for example, IRL Z44N. Okay, I don't know what it is also, but it's some component that you buy. To directly switch the ground path. 2, okay, all this was 1. 2, wiring setup, MOSFET method. This is the cleanest and most common method for independent DC electromagnets. Connect the ground, tie the negative terminal of your power supply, like we have plus and minus, so you connect the minus to the ground, GND, ground pin of your microcontroller. Connect the magnet, run a wire from the positive, the plus terminal of your power supply to one end of the electromagnet's coil. Okay, like if you have, I'm not teaching you electronics here, I don't know myself, but if you have your plus and minus, or like a car battery, you have like one is plus and one is minus, you connect like one end to the logic, to the Raspberry Pi or the Arduino, and one end you connect to the coil. Okay, like we have the coil, which is copper, and you connect it to here. This is the electromagnet. Okay, and of course the other side is also connected to something, but I don't know too well. This is not my invention. This is like a part of like very technical part. Like it's like I'm describing to you. I'm not describing how to make the battery. So in the same way, I'm not describing how to make the electronics. It's like I'm taking this for granted as if it is a given. Okay, I'm not describing this. This is not part of the invention. This is the easy part. You just need to know electronics. Or use AI like this. Switch the magnet, run the other end of the coil to the drain, the pin of your MOSFET. Okay, so the other side of your coil to also your MOSFET, to a digital pin on your microcontroller. I'm sorry, pin of your MOSFET. Now, drive the MOSFET, connect the gate G pin of the MOSFET to a digital pin on your microcontroller. In the end, it needs to be a circle. So like from the microcontroller, from this or from this, you connect also to the MOSFET. And this probably will go to the minus. For example, e.g. pin 9, add a flyback diode. Diode is like one way that it can flow, the current can go only one way and not back, not the other. Place a 1N4007 diode, bent facing the positive side, across the electromagnet coil to prevent voltage spikes from damaging the MOSFET when the magnet turns off. Okay, so like there is some diode, you paint it like, you draw it like this, if I'm not mistaken, and like you connect the diode to the coil, and this protects the coil. Of course, this is a symbol, it's not looking like this. It's just symbolized like this. Okay, so diode. 1N4007. I hope you can see it doesn't. Band facing the positive side across the electromagnet's coil to prevent voltage spikes from damaging the MOSFET when the magnet turns off. Okay, it's like this, there is inductance, and like this holds also energy. So when you close the current, like when you cut the switch off, like instead of on, then this is like storage, and it gives the energy through the wires, and this can hurt your logic component. So it's like you protect it with this, like it can go this way, it cannot go back, something like this. Okay. Again, I don't know anything about electronics, but this is like the general idea. 3 basic control Arduino code example. Here they give C++ code to program the Arduino, but I did not copy paste this. If you want, you can see in Google. I just did Google AI search, and he gave me how to program this. Okay, so as you remember from playing as a kid, 2 magnets attract each other if one is plus and one is minus, and they repel each other if they are both the same. On the other hand, iron or steel, or like any ferromagnetic thing, metal, will always attract. Okay, iron always attract. Another magnet, it depends which way it is. Which, if you rotate it, then it changes the behavior to the opposite behavior. So this is why our pins are not made of iron. Okay, our pins are not made of metal; they are made of plastic because of this. Or it can be a metal, but it does not like respond to the magnet. But again, like I want it to be lightweight, so it's not metal anyway. Okay, so what you probably did not do as a kid is to play with electromagnets. Okay, electromagnets is like this. I'm not starting to explain why when you put a coil inside the, like when you take a wire and you make it into a shape like spiral, it gets to be electromagnet. It's like every wire has, if you have a wire and inside there are electrons and they are going in this way, so they have like this law of the right hand law or something like this. If this index finger is the current and this is like I don't remember how the law works, but one is current, is either this or this, and one is the electric field and one is the magnetic field. I think this is the current. So I think the electric field is like this and the magnetic field is like this. Anyway, it gives some around the fields are like perpendicular to each other. Like if the electrical field is in one way, the magnetic field is not in the same way and not in the opposite way, it's in the perpendicular 90 degrees, 90 degrees way. Okay, it's not in the same way. It's like if this is like horizontal, this is vertical or something like this. So like it's going around, and like the electrons here are going, and there is also here around, and like all the way it's like this. And here, if you make a coil, then it's like it's going around here, and it's going around here and around here, and like all of them like make they combine, and the magnet is like, it's like there is a magnet like this. Okay, even though the coil is in this way, but the magnet is the combined magnetic field is like this. It never mind, just know that it's like a magnet. What you put on your fridge, or much stronger if you want, depends on how much loops there are in the coil and how much electricity you put it through it. Okay, so what you probably did not do as a kid is to play with electromagnets. Electromagnets are exactly the same, except for the fact that you can switch their polarity. Okay, like if this is plus and this is minus, so you can make flip the battery or connect to the other side of the battery, switch the wires, and then this becomes minus and this becomes plus. Okay, like you can change electromagnet by switching the wires. Switch their polarity, turn from plus to minus and vice versa, by reversing the direction of the electric current. Okay, like why? Because then the electrons go in this way, and instead of this right hand low, it's like the same right hand low, but now it's like this. So the current goes in the other way, and the electric field is in the other way, and the magnetic field is in the other opposite to what it was. So we want each pin to have, okay, now we are back in pins like the names, or like what I showed you before with the hand and the face, the pins. So each pin to have a range of values, like how much it is protruding or bulging or overhanging out of the tube. Okay, I will erase this so I will have a way to draw. Okay. So again, we have like our ball with many pins, and like each pin, imagine that it has a cylinder. Like through this, if we look, if this is like the book, okay, and like through the book there are pins, and this pin can be towards me, more like to here, or not towards me, like towards there. And like where it moves inside the surface of this book, it moves inside like tube, like it has, I'm sorry, it's like it looks like something sexual. It's not. It's like I'm showing that there is a tube, each part here, there is a tube that goes through the surface of the. It's like you have. I will show. Okay, so this is like a grater, you know it. It's like what you use to make applesauce or carrots or whatever. So you have the same thing but in 3D. Now imagine if it was like our board, or if our board is like this thing. This is like the middle of the board, this is the surface of the board, and here like each pin goes all the way through. I don't have something that is small enough here, maybe this. Okay, so this pencil is like going, imagine that it's going all the way through and coming from the other side. So it's the pencil, it's the pin, and it's like inside a pipe, inside a tube, like hollow tube. Okay, I hope you understand. So where is the page? Okay, I need to read faster, I'm sorry. I will never finish in this rate. Okay, so we want each pin to have a range of values. Okay, like there is a tube. It's like a pipe. But small. And inside this there is like the pin. This, like I'm showing one of them in big. Okay, this is like going inside, and it's here. And it's not stopping here, it's like all the way to here. Okay, so this is like the pin, and the pin can be, again, I'm sorry that everything looks like sexual, I will make it more normal. Okay, like this. And each and it can be like more towards here or more towards there. And there are many tubes like this. Each one of these is going through such tube. Okay, it's like the whole board is made up of these tubes. It's like Swiss cheese, like it's all made of holes. Okay? Okay, I hope you understand. So we want each pin to have a range of values, like how much it protrudes or bulging or like getting overhanging from the outside. Like, is it going like a little bit from here or a lot? Okay, is this like, okay, imagine it's like bigger, like this. So is it like so, or like maybe it's like only a little here and a lot here? Okay, like how much is it getting out? This is out, and this is in. So how much is out? And we can have a little bit out, more, a lot, and so on. like in simple words, how deep in the tube it is, and how much is sticking out of the tube. This is our equivalent for pixel brightness. Okay, why? Because like if you have all these pins out, then every place that it is out, it means that something pressed it, like our hand or our face pushed it outside. Like if we make this bigger, it looks like this. If it didn't push out, like it looks not out, like still in. Okay, and the value of how much out is like the pixel on the screen, the small square, the point of light on the screen, like how bright it is. If it is a lot sticking out, then it's very bright. It's like I'm making a parallel, like equivalent, an analog between the pixels on the screen and the pins on the board. Okay. Okay, when I say the board or the screen, it's this board, which for us is like a screen. It's made of a lot of small units like this, tube and pin. This is the pin. This is the pin. Okay, I hope you understand. This is the tube. If you saw one of these like in action, you would understand, but I'm not sure that you have seen, so I'm just making my best to convey it to you. Okay, so this is our equivalent for a pixel brightness. Like imagine a black and white screen, and each pixel can be all the way from black to white. Many shades of gray, doesn't have to be 50 laugh out loud. Let's say we want 10 shades. Okay, so like 10 degrees of how this is, like maybe 2. If it was 0, it's 1, 2, 3, 4, 5, 6, 7 until 10. It can be, we have like levels of how outside it is, how much. So let's say we want 10 shades. So we need our pixel, our pin, to have 10 different stopping stations, like a subway that goes through a tunnel. Okay, this is the tunnel, and the pin is the subway, the train, along the tube. And we control to which stopping station it jumps. Okay, it's like, it doesn't have to be like gradual. We can do like, for example, push it all the way out from 1 to 10. Like we don't need to make them like gradual. Of course, it's physical, so it goes in all the situations, but like fast, and then it stops here, for example. Okay, so it has stopping stations, and we control to which stopping station it jumps. This is physically done by having a plastic cylinder as the tube and coiling up a wire, like normal copper wire, in 10 different places around the outside of each such tube. Okay, if we have like the tube, let me use colors a little bit. Like if we have a copper, like copper is probably orange. So we have a coil, and this is one place along the tube, and this is, imagine it's a long tube. And this is another place along the tube, and so on. This is the tube. And we have like this, 10 places. I'm not drawing 10, but you understand the principle. And each one is a station, okay? Like our pin is inside here, like all the way. And like if we activate this, we put electricity to this one, then this becomes like a magnet, electromagnet, and the pin, which has also a magnet, will jump to here. If we activate this one, the pin will jump to here. Okay, it's attracted to the one we want. Okay, now. Okay, the AI first to talk to him. So this is physically done by having plastic cylinder as the tube and coiling up wire like normal copper wire. Each one like this is copper. Copper wire. And this is like electromagnet. When you coil metal copper like this, which is very conductive, and you put current, like connect this to plus and this to minus, you have electromagnet. It behaves like a strong magnet. Okay, in 10 different places around the outside of each such tube. Each little tube like this has 10 stations, 10 levels of the pixel, how bright or how much outside sticks out. Then, sorry. Spaced evenly, okay, the same space between one and the next. Like if the tube is 10 centimeters long, if all this is 10 centimeters, then every 1 centimeter we want such a shiny ring around the tube. It's not a ring, it's a spiral, but you know what I mean. And each such ring is connected to our circuit so that we can tell each pixel exactly how much to turn on. Okay, like do we want a very bright pixel like white, like all the way out, or do we want a dark pixel like black? The pin itself is also made of plastic. It is hollow, okay, like we want it lightweight. So it's a hollow plastic. So it is very light and can move fast. Like our pixels will have quick refresh rate for our screen, for our board or screen. We give them the command, they move fast out or move fast in. If they have a lot of mass, then there is momentum, it's hard for them to move. And in the middle of it, it has permanent magnet. Okay, the pin itself, in the middle, it has magnet, like if we draw a magnet like this. Okay, like maybe this is the north and the south. Like plus and minus of magnet. So here we have in the middle of this pin, we have such a magnet, like not electromagnet, a permanent magnet, a normal magnet like this. Okay. No. Okay. And also like here, I did not draw this, but here also there is a big pin. Let me draw it. And in the middle of this pin, there is magnet. Which again is north and south. A normal magnet I am sure you played with as a child. Okay. So this is like a normal magnet. We don't need electricity for this, we need electricity for all the electromagnets, the coils. It has permanent magnet. And in the edge where the user will touch it, like here, and here also, the user will only touch this, but we can do them both rounded. Like the head of the sewing pin or the head of the nail, it is rounded, like a dome, which is pleasant to the fingers. Not sharp, not pointy, so you go out, it's like round. For the magnet in the middle to be strong, we can epoxy there, we can glue neodymium NdFeB magnet. Okay, so neodymium, it's just some metal. Like strong permanent magnets are made of this metal. Neodymium, the formula is neodymium ferrum B, which I don't know what it is. This is neodymium, this is iron, and B I guess is boron, but I'm not sure. I think boron is. Okay, this is the better implementation to do this. If you insist on another more complicated, you can think of like how the spring of the pinball machine works. When you start the game by pressing the electrical button, okay, you know what the pinball machine is. You have like flippers, like here and like here, and like they flip, and you have like a ball, and the ball like goes hit something and goes and like make all kinds of path, and then comes back and you lose your money. But anyway, when you start the game, you have a button and there is a spring, and the spring, like when you push the button, the spring is it has like some magnet or something that pulls it, and the spring is pressed, like stores energy, and when you click push the button or release the button, never mind, the spring lets go and the ball flies and like goes all the way here and starts all the movement. So this is pinball, and I think you know it. So I'm trying to explain with things from life, from everyday life. So the other implementation, not this one, this is the good one. This is more complicated, also good, but complicated. So you can think of like how the spring of the pinball machine works when you start the game by pressing the electrical button and then releasing, and the spring pushes the ball. So we can do this with each pixel being a flexible Bowden cable. Take Bowden cable. It's like in old cameras, it's like lets you push and pull, but from far away, like a chain, but chain can only pull, and Bowden cable can also push. So from far away. So like in the old cameras, okay, you have the camera, and it has, I don't know, this is the camera, and you have here the button, but you did not want to move the camera because it was very sensitive. There was no movement cancellation or anything. If you moved it, it ruined the picture. So you could buy a Bowden cable, and then you have this like syringe, and you press it, and it was like a flexible pipe that is connected to here, and here it would press for you. You press here, and this press here. Okay, like it gives all your force of your finger to here. Without, you don't need to touch here and make the camera move. This is like how it worked. And this is called Bowden cable. So each one is like a combination of how we made this and how we made this. I'm connecting for you the ideas. So we can do this with each pixel being a flexible Bowden cable that you can push and pull from far away. Like the old cameras, that in order not to move the camera, you would connect such device. I will take chocolate so I will not faint on live broadcast. 1 second. Sorry. So from time to time I will go to fuel myself. Then you can give each pixel an actuator. Actuator is tiny motor which controls it independently. and the motors do not have to be tightly squeezed together. The pixels must be packed very close to each other, but the motors no. They can be more, they have room to be far away from each other. Not far away, but not really like sardines, because the flexible property of the Bowden cable allows them to have more space between them. I'm not getting into this, but if you're interested, like each one each tube has a pin, and this pin and this pin, each one is connected to a motor. I don't know how to draw a motor, but let's say it's like never mind, this is like a motor, and the motors can be like far away from each other, and like they can give the power, the push to the pin for a Bowden cable. Like this has a Bowden cable from here, this has a Bowden cable from here, and this has a Bowden cable from here, and they don't have to be next to each other. But of course, the pixels that we see, that we touch, sorry, the blind touch, they must be close to each other. But the motors can be more far away from each other, which is important because they are not tiny. They are tiny motors, but the motor is not like a pin. It's like needs more room also to breathe. It's like releasing heat. Okay, if we make them too close together, they will also burn, and also they are not so tiny. Okay. So this is why it's important that the Bowden cable is flexible. And it takes this power, like the power that controls this movement, the electromagnet movement, but it transfer it farther away, like from here to here. Okay, so here I hope I convinced you that it can be done. Okay, now all this was building block 1. Now, but don't worry, this was the big one. Now building block 2, scrolling. Okay, what is scrolling? Like in games, old games in DOS, not in Windows, you have like you are moving along the screen, and your person or your character is getting to the edge of the screen, and then it needs to continue. So all the drawing, all the painting of the background is like moving as if you are continuing, but it's the same screen, but the graphics itself is moving. Like if this is your person and he's moving and he's here, so the graphics is like scrolling so that it can continue. I hope it's clear. Just look in Wikipedia what it means. Scrolling. In graphics, computer graphics. Okay, so when a sighted, not blind person is looking at some scene, he turns his head to the side and see the next part of the screen which was not visible to him before. Because we have like 180 degrees, but like if we want to see what is here, we need to turn our head. Because we have like 180 degrees field of view, FOV, from left to right, and we have like 100 degrees from up to down. 100 is like 90, like this, a little bit big. In computer graphics, we do this by scrolling. Like in platform games, the hero runs to the side and we see more of the scene revealed smoothly. What we need for the blind person is that his field of view, which means our whole board screen, will move according to where the blind person rotates his head, and his hands will have to follow the board slash screen. Okay, so like if this is, I'm sorry for the low tech technology, but like if this is the screen and like I move my head to here, like if I'm a blind person and I moved my head to here, then this needs to move here. And I will touch it when it's here, and if I do not follow with my hand, then I'm touching air. And I need to be alert and like to follow. It's not happening quickly, and it happens only when I turn my head. But when I turn my head, it's going with my head. Why? Because the computer will tell it to go physically in the real world to here. I will explain how. Where the blind person rotates his head, and his hands will have to follow the blind man's hand. Hands will have to follow the board slash screen. This is really simple to do. We just need the screen not to be mounted on a wall or sitting on a desk, but instead the screen needs to be mounted on a small platform with 4 wheels, something between the small but smart remote control toy car that a kid have, and between the big but dumb service cart that his mom have, that she puts refreshments for the guests on that. Okay, like you know, like a coffee table but moving. So this big, and like but on remote control, that it can move. Not that it can move, that it can be commanded to move by the computer. This is more correct. Okay, so in Wikipedia you can look in radio controlled car, and in Wikipedia also you can look in serving cart. Okay, radio controlled car. Okay, so it's like a combination of this plus this. This plus this gives us our moving system. Okay, but this moving cart needs to hold out board screen in any angle. Like if this is the screen, it needs to be like an arm, like a hand, mechanical, that like hold this, like maybe it moves like this or like this, or like to this side or this, like it needs to be able to hold this in any angle, because the blind person might be looking left, right, up or down. So the wheels need each to be able to turn separately, and it should be able to circle around the user. Okay, like let me erase this. Okay, so let's say we have like our card. Okay, so it has wheels. And it has wheels here also. Um, and I'm sorry for my drawing abilities, or like lack thereof. But this is our card, and like the wheels need to be turning in every direction, like a supermarket cart. Okay, like that you can move it to the side suddenly, and the wheels will turn and will be like this, or like in another end, like a supermarket cart. It's not like a car. It's not like you can only drive forward and then turn like this. You can suddenly decide to move it in parallel to how it was, and it's working. So this needs to be with flexible, not flexible, like rotatable wheels. So not with a fixed axis, they can turn the axis. Why? Because like if you look at the room, if this is the room, from above, okay, bird's eye view, so if we have the person in here, and we have the card in here, then we want it to be able to move like it cannot drive like a car and drive only like this. It needs to be able to move, like if it needs to move from here, let's say it's here now, and it needs to move to here, then the wheels need to turn like in the right direction, all of them, like that it moves. I hope you understand. Like not like a car that only the front wheels can do this and the back wheels are always forward. No. In this thing, we need all the wheels to be able to rotate. Let me see if I close the shutters. Yes. Okay, and then we'll see the other torch. Once again. So now we continue. Okay, so the wheels need each to be able to turn separately, and it should be able to circle around the user. Okay, it needs to be able to do like this around the user without problems wherever the user is looking. If the user is looking like to here, it needs to be here. If the user now is looking to here, it needs to go around the user, but like to face the user. Okay? To face him with this arm that holds. Like if I'm the small card, then and you are the user, then I'm always towards you. If I encircle you, I am like encircling you in a way that you can always see, touch this. You cannot see because, God forbid, you're blind, but you can touch this. Okay. So, because the blind person might be looking left, right, up or down. So the wheels need each to be able to turn separately, and it should be able to circle around the user, not just go forward, backward like a normal car. This is not hard to do, but we do need to here I missed the word. We do need to let the system to see the user, not to run over him or step on his toes. Okay, so of course, like we don't want the small card to hit the user and not run him over and not hurt his small toes in his foot. Like he needs to be safe. So this like needs to be with some way to see. The blind person cannot see, so we need to protect him. Anyway, any person we need to protect, but especially a blind person, we need to protect him from this. So this needs to see with the camera what is going on. So we have a camera like CCTV camera or like webcam. It's not like a spy movie, it's like webcam. That controls this, but one camera is not enough because you cannot see, like, okay, you can see maybe left and right, but what about forward and backward? It's not good. So you need two, like we have two eyes to see 3 dimensions. So another camera like here. Okay, they are not in the same place. And maybe like he's hiding. Like if the camera is here and the car is here, it is hidden, but the camera from here will see. And the computer, will understand. So we have another camera here. Okay. So the system has a webcam that continuously monitors the user as the user moves. Okay, the user is not always here, maybe he's moving, like he's walking, it's a person. Maybe he's moving, so the car needs to be careful not to hurt him. And still to be close enough so the user, the blind user, can touch this and feel what the car is holding, the board, the screen. So the system has a webcam that continuously monitors the user as the user moves. So we know where his body is at all times. To get the 3D of where he is, 3 dimensions, we can use one webcam from the front and one from the side. The webcams do not need to be on the car or card. the webcams can be, for example, one on the desk and then the other on the wall. The webcams transmit, broadcast their video feed to the computer. The computer analyzes where the user is in the room, and the computer gives the card/card instructions on how to move now. Okay, so like there is a computer. Okay, don't know how to draw the computer, like and the computer controls with the antenna. It gets information from here. It gives information to the card, and the card knows from the computer how to move, so not to hurt the person. So as for the arm with which the card/card is actually holding the screen board, okay, like this arm. The arm is sitting on the card, so it needs to, the card is holding with the arm the board. So we are now talking about this arm. I think we should have two rails vertical, like sturdy, made of light metal. Okay, so on the car you have like two rails that, like if we have a cogwheel, okay, this is cogwheel, it's not a sun, and this is rail. This is also rail. So the cogwheel can go up and down. Like I think we should have two rails, vertical, like sturdy, like frame, made of light metal, like aluminum, with holes in them, so that cogs can drive up and down from almost floor level up to almost ceiling level. In parentheses, or the height that the user's hands can reach, to be more accurate, close parentheses. And from these two vertical rails, we need to have two horizontal rails. Okay, so from this, I will make them in different color. So we have, for example, okay, I hope you can understand that we have like the same, but instead of vertical, this is horizontal. Two rails, like one, two. And this is like we have in a reprep, or what it's called, that you have like a CNC machine, like a computer, something control, okay, like, or like 3D printer, you have a possibility of the arm to move in this way and in this way, like coordinate system in one direction and in the other, but they both need to be in the same machine. So here it moves up and down, and it also moves forward and backwards. I hope it's clear. This is like, I did not draw it like good, it should be like towards forward, okay? Maybe I should draw it in perspective. I'm sorry, I'm so very wrong. מה? היי. לא. אז ביי, אני מקליט. אז ביי. ביי. תודה. Okay. So now I will draw this better, I hope. Okay, so it should be like in the same direction as this, like forward. Okay, if the car is going forward, then the direction of the rails is also in the same direction, like this. And like this. Okay, I hope now it's better, little. And again, there is cogs. And the cogs can move the arm that holds the, you find the arm that is holding the screen or the board, then the cogs can move me up or down on this, the vertical, and forward and backwards, like towards you, forwards and backwards towards the user, away from the user, with this, the cog wheels turn to here or turn to here. Maybe I did it the wrong direction, but you understand. Okay. Basically, we are building like a forklift structure. So from now on, I will call the car/cart forklift. Okay, so if you don't know what the forklift is, we will call all this forklift. This is the forklift. And a forklift is like a car, but in factory. That has it's holding something. Like for example, it can hold a barrel. Okay, it can hold something heavy. It goes down, it moves below the heavy thing, and it lifts. Okay, so this is a forklift, and this is like how we call the whole car/cart. I will not call it car, I will call it forklift. Because again, the arm needs to go up and down like the fork of a forklift and the whole thing carries something like a forklift. Okay, so the angle to the side, left or right, is done by the movement of the actual forklift encircling the user. Okay, like I walked, but if I'm in forklift, I drive, like I turn my wheels and I drive to here around you, you are the user and I'm driving to here. So this gives the angle. I do not need to make like this angle and this angle. No, I'm moving myself and the angle is fixed. What we do need is up and down, which we will talk about now. Okay, so the angle to the side, left or right, is done by movement of the actual forklift encircling the user. But not, I'm sorry, but how do we get the movement of up and down, like when the user lifts his head to look more up or lower his head to look more down? Okay, the user is looking down or up. How does this work? This is okay. This movement that if the purple ones go up along the vertical, like the forklift lift the arm and then up. So now it cannot be like this. It needs to be towards the user who is down here. Or if I'm going down, then the user is here and I need to show him the screen so he can touch it. I cannot do it like this. I need to point it to him. So this needs to be here in this angle, and this needs to be here in this angle, and this needs to be here in this angle. So how do we make this angle? Up or down? This is done easily by the forklift having, instead of just one fork, okay, this is one fork, two arms, this is called one fork. From below, it also has another one fork from above. Okay, like usually forklifts that are like this and are holding a barrel, they also, or anyway, some forklifts have another, like another fork. This is fork, and this is fork. Okay, like fork 1 and fork 2. And it has two forks. Each one with two arms. This is one fork and the other one is another fork, and together it's like 2 arms plus 2 arms, 4 arms. Okay, so this is done easily by the forklift having, instead of just one fork from below, it has also another one fork from above. What this is giving us is enabling us to hold the board / screen in the grater. This is a grater. It enables us to hold it in any vertical angle that we want, from pointing upwards, like raised relief map. Okay, relief map. I don't have time to explain, I will just write it, and if you want you can look in Wikipedia. It's like 3D map. Okay, it's like 3D map. Not flat map, but a map that is like with mountains, valleys, and so on. sometimes you have it in the classroom in school. What this is giving us is enabling us to hold the board/screen in any vertical angle that we want, from pointing upwards, like raised relief map. You can see in Wikipedia this term, like the sand table that generals use to plan military operations. You always see in movies, especially old movies, they have like all the generals are around table with miniatures, and they move the force, the troops, and they put like a tank here and like the base there, and like they simulate. So this is a sandbox. I'm sorry, not sandbox on computers. It's like sand table. So like the sand table the generals use to plan military operations, 0 degrees, 0 degrees. The map is lower than the user, the map faces upwards. Okay, this is like a table that is facing us, like we are from above and we are showing the user from like this, it's facing up. To a 3D map, like what they have I made a mistake, have in classrooms, like the map of the country, but in 3D, 90 degrees, 90 degrees, vertical. The map is in front of the user, in his eyes level. The map is facing sideways towards the standing user. Okay, if you are the user, if I'm the user, it's facing to me, sideways. If you are the user, it's facing to you, forward. It's not upwards, it's not downwards, it's sideways. And all the way to like a panel on a spaceship or a submarine, which is on the ceiling and facing down. Okay, this is 180 degrees, like it's on the ceiling and we can touch it from below, and it's facing us, it's facing down. The map is higher than the user, the map faces downwards. The equivalent feeling of scrolling, like we see the animation of the same pixel moving on the to the side, is done for the blind person by the actual feeling of the pin moving to the side. Okay, like if he's moving his head, like from side to side, for example, then me, the forklift, the car, is moving. You are the user, I'm moving. Like if you moved your head to here, I'm moving to here. And you feel like the pixels going away from you, and if you don't move your hand and come with me, then you miss the pixels. Now you have to be like, it's moving, you moved it with your head, but you need to follow with me. Follow me. Okay. Of course, the blind person needs to walk and adjust himself to follow with his hands the movement of our forklift, in parentheses, which was caused by the person turning his head, close parentheses. The person's hands should always be in front of him. Okay, all this was building block 2. Now building block 3, depth. Okay, depth. Let me erase everything and write it down. Okay, so building block 3, depth. Okay, so we all know when playing computer games or watching a movie, on the same screen, your only screen at home, the monitor, the camera can travel forwards or zoom to where we are headed. And this is not scrolling, it's not sideways, it's like towards you or away from you. This is 3D moving forward. In normal 3D, this is done, if you can see, if you are not blind, this is done by displaying in proportion. And when scrolling, we apply parallax. Okay, so proportion. And proportion is like if you have you see two rails of a train, and like in the horizon it looks like they are coming together. Like you see it here, and like here it's like visually it looks like they come together, even though you know that it's not true, they are still parallel, even here. But it looks, because of perspective, I'm sorry, I wrote proportion, it's not good what I wrote. I'm sorry, perspective. Perspective, not proportion. Like it's a related concept, but I guess, but it's not the same. I used the wrong word. So perspective, I'm sorry, perspective. And when scrolling, we apply parallax. Parallax I will just explain it like I explained here. Like in the same way that when we drive in the car, the things that are close by on the side of the road, like utility poles, like electricity poles or telegraph poles, and road signs are passing us by quickly. Like if I'm a car and this is a traffic light or something close by, it passes me quickly. While the things that are far away, like far mountains, move slowly. And the distant moon, like the sun or the moon, seems to almost not move at all. This is parallax. Okay, but how do we do this for our blind person? Okay, he doesn't see. He cannot have these tricks of 3D. What do we do for him? We cannot simply draw. I'm sorry. We cannot simply draw on the very same screen something close and something far away, because it will mix for him in his mind and confuse him. Okay, like in a normal picture, we have like a picture from the window of the car that is traveling, or a train that you are sitting in the train, and you have like from the window you see the moon, which is far away, so it's not moving at all. You see the mountains, which are moving a little bit because they are far away, and you see the trees from closer, which are moving very fast, and the poles of the electricity, for example, are moving like very fast. They are like, you understand? So this is parallax. But if we draw all this for the blind person with the pins on this, if we draw all of these layers, he will get confused because he doesn't know that this is far away, this is close, it's not, he cannot get the parallax like this. Okay. It will confuse him. So what we do, so this is not good. And this is not good for a blind person. So what we do, is we give him slices, like cutting a cake, slices of reality. Okay, like we are cutting a cake to pieces. In the same way as a computed tomography scan, CT scan. Like CT scan. Okay, in the hospital. Scan the object, like slicing our brain, for example, and display to the doctor each slice separately. You know, like you have like the 3D brain, and like the doctor sees some slice, and maybe it looks like this, and like another slice looks like this, and so on. It's like he's seeing each time one slice. The doctor flips, I'm sorry, like slicing our brain, for example, and display to the doctor each slice separately. The doctor flips from one image to the next, going deeper forward or more shallow backward. Here we do the same. In our system, we do the same. We display to the user, to the blind user, we let him feel, not display, but we make him feel with his hands each time the view of only the current depth, what is now, this slice that we are looking now. For example, to a real picture, the AI model of Quen image layered is doing this automatically. Okay, Quen image layer. It's an AI, artificial intelligence, to do this for visual pictures. Is doing this automatically. But in our use case of making up a virtual scene, like we do in virtual reality VR, anyway, everything is modeled and then rendered. Okay, it's computed and then it's drawn. And things are ordered by Z distance, like what is close, what is far. Like in order not to draw far away things that are hidden behind other closer things, okay, so we use this Z buffer. So here we use the same algorithms, but in order to split the picture to layers. And of course, instead of drawing, we are making the 3D touch haptic raised relief map. Okay, like the blind person cannot see, we are making this with the pins. Okay, so in this depth, when it's zooming, the board will not move. I will explain soon what will happen, but if you are in close by, the pins will make some picture. If you are now moving to another zoom level, you are saying, I want to see more far away thing, then the picture will be made something else, but it's the same board. Okay. So how do we know if the user looks closer or far away? We do not want him to get away from the board/screen, because then he loses touch with the information. Like if we say, okay, like in virtual reality, normal virtual reality, you step forward, you step backwards, but we do not want the blind person to walk away. Like you walk away from the board, you cannot touch the board anymore, so it's not good. You cannot feel, you lose the information. So we need to make some other pattern. Okay. What we do is we analyze if his hands are more outstretched or like pushing away something far away from us. We stretch our hands forward, or the elbows are bent and his palms are closer to his chest, like the object is near to him. We do this in the same technology as laser harp. Okay, like harp, the instrument of musical instrument, but laser harp is like a harp. Normal harp is maybe looking like this, and you have like two, it's a frame, like you have like this, but you have strings connected. So instead of strings in a laser harp, here it is open, and instead of strings you have lasers. Like instead of each string you have the laser going from here to here, a laser going from here to here, a laser going from here to here, and you move your hand with a glove so you will not burn your hand. And when you cut this laser, he knows, and he plays some sound. When you move your hand to here, he knows, and he plays another sound. When you move to here, another sound, and so on. This is laser harp. Okay. So you can look in Wikipedia, it's interesting, but not now. Like if you imagine the sand table of the generals, then a little above it, like 20 centimeters above it, we have lasers. They do not need to be visible. Okay, like the lasers are not going up. They are, if this is the flat, if this is the flat sand table, the board, the screen, then like up here there are lasers. Like here, this laser going to the side, this laser going like a grid of lasers to here and to here. And they know where your hand is. They feel it. Okay, it's the same principle like this, but lying down. Or anyway, parallel to the board. Like if the board is like this, then the lasers are here in the same orientation, parallel to the board. Okay, so like if you imagine the sand table, then a little above it, like 20 centimeters, 20 centimeters above it, we have lasers. They do not need to be visible, they just need to be not dangerous, safe. And they need, and then need to detect, to know where is the forearm of the user. Not the palm and the fingers, okay, not this, the forearm. Not the palm and the fingers which are on the pins, the forearm, which tells us if the user arms are stretched out or bent close to him. Okay, like if the lasers, if this is the board and the lasers see that, okay, my forearm is like just like a straight line minimal from each direction, then it means I'm like pushing, like I'm showing very little forearm to the lasers, like only the lasers that goes here and goes here feel this. But if my forearm is like this, then this laser see, and this laser see, and this laser, and this laser, and this laser, and this laser, like maybe I showed it the wrong way, but you understand that like they know how your forearm is, if it's like this or like this, if you are close to the board or far away, and this gives us the depth. According to this, to how you hold your hand, that they know because of the lasers, they will show the correct slice, the correct depth. And from this, we know exactly how far away the user wants to look, the blind user wants to feel. This is like the focus or zoom, zoom in, zoom out, to far away distance or close. We need to check if protective eyewear is needed against the lasers, because like if a blind person has 10% vision, we do not want to hurt the little that he have with lasers. Okay, this is obvious, but I say it anyway. Of course, if, just to make sure that you understand. Of course, if lasers pose a problem, we can do this in many other ways, like to know how the forearm is, like sensors that transmit the angle of the lower arm, of the upper arm, and they transmit the angle of the forearm, like this, for example, and I wrote here Adafruit, 9 degrees of freedom, absolute orientation, IMU, I don't know what it is, fusion breakout, BNO055, ID 2472, Adafruit, industries, unique and fun DIY, do-it-yourself, electronics and kits. And I give you the link. Adafruit.com, product 2472. Okay, so you can look in the website of Adafruit. They are like a company of makers. They are called after Ada Lovelace, the Countess Lovelace, the daughter of Lord Byron, who was the first software programmer. She was the first programmer in the world before there was a computer. So they are named after her, Ada. And 9 degrees of freedom. Absolute orientation. Okay, I don't want to write this, it will take me an hour. Just write product 2472. Okay, 2472. This is like the product number in their website. Adafruit.com. Okay, so now building block 4, surround sound. Let me erase the board. Okay, I want to see, just to check if there is electricity in the microphone. Okay, not much, so I will need to talk quick. I did like almost half and it's really bad. I'm in page 5 out of 9, so I need to move really fast forward. Okay, building block 4, surround sound. I hope I don't have mistakes in the spelling. Sound. Okay, so I'm reading fast now. I don't want to run out of time. There's also limit to how much YouTube is willing to record. The user can hear each time the sound of what he is looking at, looking in quote unquote, like double quotes, because like he's blind. So he's looking at where he's turning his head, then this is where he's looking. So the user can hear each time the sound of what he is looking at, because on the forklift, the car, we put speakers. Okay, speakers. On fork. Because on the forklift we put speakers. There is no need for surround system with many speakers. The same 2 speakers stereo are surrounding the user by doing circles around him. Okay, when we are moving around the user, I'm with the speakers. I am the forklift. I am the car. I have on me the speakers. So the speakers are moving around the user and below him and above him. 360 degrees times 360 degrees. Okay, so like this. What sounds do we play in the system? If it is a realistic scene, then obviously the sound that he hears from the direction that he is pointing at right now, and from that distance that he is pushing right now. In this way, he can scan a busy street scene without being overwhelmed by hearing all the sounds at once, not being able to detect which sound comes from which location, because we see also with the eyes, the blind person, like, it's hard for him to know exactly. Okay, but what if we want to do a scene which is more abstract? Like, for example, teaching geometry or something. Here, I think we should use the lasers that are above the screen / board. Okay, remember we have above the screen or board, we have lasers. So here we need to use the lasers. When the user just hovers above the screen / board, so the current depth becomes locked, okay, like locked, we are in the same depth, not caring about this anymore. And the user's palms of his hands are like in scan mode of the shape, okay, of what is on this, on the pins here, he scans them now. We do not want the user to scratch his hand touching the pins. Like, if we want him to scan like all the pins, he will scratch his hand and like injure himself. So just like a sighted person can hover with the mouse arrow, like you have tooltip or something, you do not click, you just hover, you wait with the mouse above the text, above the interface, the GUI, like above the button, and you see tooltip, this button makes blah blah blah. The blind, so just like this, the blind user can hover with his palm of his hand. What he gets then is not touch, because he's not touching anything, because it's above the board, it's like here. He's not here, he's like here, it's only touching the lasers. The lasers know where his palm is, what he's doing. And what he gets then is not touch, because he's not touching anything. He gets a more accurate scrub of the surface. Okay, scrubbing. Okay, scrubbing is like not polishing, like rubbing. It's like rubbing in audio. Okay, like you go forward and backward on the waveform of what you hear. Look in Wikipedia, because I will not have time if I will explain everything, I'm sorry. By scrubbing, he can get, but in any DAW, digital audio workstation, you have this, it's very basic. There are like 3 ways to do it. One of them is good for us. By scrubbing, he can get the sound of the picture like a sound wave. And unlike the physical pins, in scrubbing mode, we can offer the user's ears much better resolution, like how many levels we have in that sample. Not just the 10 different levels that we have with our magnets. Okay, remember we had like the stations of the subway, we had 10 stations, but in wave of audio we have like, I don't know, like thousands of discrete levels that we can hear the quality. Okay. Okay, so by scrubbing, he can get the sound of the picture like a sound wave, and unlike the physical pins, in scrubbing mode, we can offer to the user's ears much better resolution, like how many of, compared to how many levels we have in that of how many levels we get in that sample, and not like compared to the 10 different levels that we have with our magnets. We have a lot more. When we scrub, we can make him hear a lot more than what he can feel in touch. Better nuances, better resolution. Like instead we said like 50 shades of gray, like 10 shades of gray. Here we have thousands shades of gray, or 10,000 shades of gray. Okay, so the scrubbing, the pixels are more giving more colors. It's black and white, but it's more shades, more this kind of gray, that kind of gray, a lot of different grays. So the scrubbing is not just for fun, it's like the user's way of zooming in into finer details, equivalent to the reverse pinch of a photo by a sighted user on the phone. Of course, we can also apply such gestures, like the pinch that you make zoom or zoom out on the phone. The system should be customizable so that the user can decide how to zoom in, and we will and what will it actually do. Okay, when it does this or this on the pins, what will it give him? Will it give him like the scrub, the more details? Will it give him like the slices? It needs to be flexible. It's easy to make it flexible. Maybe he prefers to feel more distant objects. It depends on the specific application. Is depth more important than fine details, or the other way around? It's like there are glasses for reading close by and glasses for driving to see far away. So he needs to, he maybe wants this kind of glasses, that kind of glasses. So we need to enable him what he wants to choose. I think with time, the scrubbing can be almost as intuitive as bats, okay, like flying bats, like Dracula, no, that's a vampire, or bats or dolphins navigate with sound. Okay, I think with time, the scrubbing can be almost as intuitive as bats or dolphins navigate with sound. Like sonar, like with practice, the user can wave his hand, similar to how we signal hello, but the sound will already tell his mind, this is a triangle this big, rotated in this angle, and it is congruent to another triangle that my other hand is scrubbing above, because they make similar sound pattern. Okay, even if this one is rotated in another way, but they make similar patterns. For the brain will know with practice. For example, then he can touch the triangle and verify slowly, like make sure. Like there should be a mode of the system, future improved, like there should be a mode of the system. Okay, I don't know what I wanted to say, but I missed the sentence. Okay, next sentence. Future improvement that is easy to do is to give each hand its own separate board, screen/board. Okay, like we have two boards now, and like our forklift is holding for you, you are the user, and you have now two panels, like two boards with each one with many pins, and you can put your one end here and your other end here, and you can touch like two at once. They don't need to be close together. You can touch here and here, like wherever you want. In this way, a blind person can be more powerful than a sighted person, similar to how a chameleon, okay, chameleon, you know, this animal that changes color. But here I'm not talking about the color, I'm talking about how each eye of the chameleon can turn on its own. This can turn here, this can turn here, like they are not connected. They don't need to move to the same direction. They can go like without connection between them. So in this way, a blind person can be more powerful than a sighted person, similar to how a chameleon can move each eye to another direction. Chameleon's eyes are independently mobile. I'm not talking about I go, haha. Okay, it's like a joke when you close your eyes. Okay, by the way, this can be used as advanced GUI, like interface, for sighted users too. If we use the movement of the pins inside the tubes to generate small currents, electricity, and in this way to analyze where the hand is pressing. This is not simply like a touch screen that follows your hand all around you and above and below you. This is stronger in some sense because it has depth. You can press into it a lot or a little, the 10 centimeters depth, which a touch screen is flat and does not have. Combined with the lasers above the screen, the depth can be much more, as we already discussed. Okay, as you remember, I promised you in the beginning two inventions, both based on office toys, and so far I only described one. Now we will explain another invention that lets you touch the finer 3D details of small objects that are the scale of your fist, that can fit inside your palm. Okay, so now I will erase the board and we will do quickly another invention. Not quickly because it's not important, quickly because I'm afraid that we will get stuck without all the video. Okay. So this is like the second invention. I didn't decide how to call them, like one is VR2, virtual, and one is voxels, blind voxels. So you can call it what you think is best. Okay. So now we will explain another invention that lets you touch the finer 3D details of small objects that are the scale of your fist and can fit inside your palm. So the building blocks that we need to understand for the second invention are building block 5, hydrophobic scent or magic scent. Okay, I explained already that you put your hand inside. When you put the sand above the water, you put your hand inside and it's like isolating you from the water. You do not get wet. So hydrophobic sand or magic sand. This powder prevents the user from getting wet even in the water. It's like forming a surface around the user, around the finger's hand. It's not crucial to the invention, it's not, you don't have to use it. It's just nicer feeling not to get wet each time you visualize something, especially that a non-Newtonian wave, not wave, I wanted to say liquid, is usually something icky, like disgusting, like custard or ketchup. Okay, so you can see hydrophobic sand in Wikipedia. Okay, building block 6, next one, non-Newtonian fluid. Okay, non-Newtonian fluid, non-Newtonian fluid. This liquid responds by being soft, like water when you move slowly inside it, or hard as concrete when you move fast inside it. For example, custard. Okay, like think about it like even water. When you go slowly inside it, like when you're swimming, it's very soft. But if you like fall from, I don't know, the 10th floor of a building into the pool, you will die because it's like concrete, because you come very fast. The water particles, molecules, have no time to move. They like hit you and you are like dead. So, and if you jump from the standing next to the pool, nothing happens to you. It's very soft. Why? Because then you are in slow speed and like the water has time to move. So non-Newtonian liquid is even more like this. Even in small speeds, it needs to be very slow for it to be soft. If it's even a little bit fast, the movement, then it is hard. Okay, this, non-Newtonian fluid. This fluid responds by being soft like water when you move slowly inside it, or hard as concrete when you move fast inside it. For example, custard. Custard is like something that you make with eggs. It's like thick, like viscous. Non-Newtonian liquid is always viscous, like not flowing easily. There is a nice demo of this in this YouTube video. John Tickle works on custard. Brainiac. Okay? John Tickle. Works on custard. Okay, this is by the British television show Brainiac. Basically, you can be like Jesus but not on regular water, only on something like non-Newtonian fluid like custard or ketchup and so on. When he walks, the impact of his feet hardens the liquid, and the surface of the water, it's not water, it's custard, but the surface of the custard is hard and it holds him, he can walk on it. And when he does not sink, when he stops and simply stands still, then he sinks. Okay, now building block 7, wave pool. Okay, I will erase the board and explain. You know what, no need to erase the board, I will just explain. Wave pool. Of course, miniature, the size of a fish aquarium box, not a real swimming pool. Okay, so you can see in Wikipedia what is wave pool. Of course, you know, but just to make sure we are on the same page. Okay, I'm sure everybody saw a wave pool simulating the sea, creating waves. Even surfing there, you can surf. And sometimes they are used for more serious stuff, like solitons, like a wave that, one-dimensional wave that does not stop ever. It's really interesting, but we don't have time now. But I'm talking about an aquarium-sized tank, okay, something like 1 meter on 1 meter, that has engines with pedals, pistons, that can push water exactly as the computer tells them to. In parentheses, the computer controls the engine / servo is like engine of robot, something that is controlled, of each pedal. Okay, like there's something that pushes the water and this something is controlled by a computer. And when the water meet each other, the waves cause interference. Okay, let's write interference because it's really important. Okay, like in a lot of inventions of mine, there is interference. Interference is like you have one wave and another wave, and when they meet, they either cancel each other. If they meet in some way, they make each other stronger. If they meet each other and cancel each other, then it's like nothing. Like it depends on what is the phase between them. I'm not explaining now, but you should see in Wikipedia about, if you don't know, about interference. It's very interesting and important. And when the water meet each other, the waves cause interference, okay? One pedal pushed from here, one pedal pushed from here, there are waves coming here, there are waves coming here. When they meet, it depends. Maybe they will do something twice as big, maybe they will do cancel each other out and there will be no waves at all. By interference, I mean constructive interference, when it's making bigger waves, combining smaller waves into bigger waves, or destructive interference, combining waves into areas of calm, nothing, and silence, where they cancel each other. Here we are talking about not sound, but about water, like custard waves, physical waves of liquid, non-Newtonian liquid, where they cancel each other. Since this is all done inside a small volume, we are not trying to predict like the climate with turbulence or something like chaos and where a butterfly effect and like a small movement here makes like the flap of the wings of a butterfly in Brazil cause a tornado in Texas 2 weeks later. No, here it's like really small. We can predict what will happen in this small, in crude way, not in the molecule level, but in small, I'm sorry, in crude way, in rough way, more or less, we can know for sure what will happen and compute with the computer. Okay, so since this is all done inside a small volume, we are not trying to predict like the climate with turbulence or something. The crude calculation that the home computer do are enough to know how to create a peak or a trough, I don't know how to call it, like the opposite of a peak of pressure in any point that we want in the water, by combining different engines slash servos in different precise timing. Okay, like if we look at the pool, small aquarium that we have from above, from like how it looks from above. So let's say it's like it's looking like this, and here there is a pedal that push to here, and like it makes waves like so, and we have like, I don't know, like here one that is pushing to here, and it makes waves like so, and we know what will happen here because we know when we activate this, if there is phase different, timing difference, size difference, we know everything in more or less, not in the atom level, but in the big wave we know, in a 1 meter pool we know enough to make what we want to do here. Since this is all done inside a small volume, we are not trying to read it already. Okay, this is similar to what we do with light, where instead of a lens, we manipulate the waves with diffraction grating. Okay, I'm just writing, I'm not explaining. Okay, which works like lens. Okay, with lens we can focus the light, we can bend the light, we can manipulate the light. With diffraction grating it's the same, and we can, like if we have on this wall a few servos, engines, we can push the water in such a way, like this one, and after this one, and after this one, that it will behave like making the angle of the wave to here or to here and so on. Even though they are all pushing forward, but because the first one started and already propagated, it's like it's complicated, but we can do it. The computer can do it. Okay, so as you know, but here it's not light, not visible light, here it's like physical waves. Okay, so as you know, in many movies, there is this trope, like recurring thing again and again, of the hero submerging himself in entering into liquid and then gains some deeper understanding of reality. Like for example, in Stranger Things, 11, the girl is in a tank of water. In Dune, the navigators, okay, the ones that fold fold space, float in some orange spice tank. In Minority Report, the precogs are in some milk, photon milk. In Constantine, he submerges in water to see hell. In Riddick, the elemental seals live in some liquid baths. Okay, probably there is more movies, but I don't get to watch a lot of movies. But this always either is based on nonsense or on a concept of isolation tank, sensory deprivation tank. Like that you detach yourself, disconnect yourself from your body's senses. Okay, so isolation tank, you can see in Wikipedia. Okay, so we are getting insight and vision, but we, in my invention, are getting insight and vision, but in exactly the opposite way. Okay, not in isolation, not in detaching ourselves, disconnecting from our senses. We are connecting to our senses. We are doing the opposite. We immerse our blind user's palms in liquid in order to give him more haptic feeling. Haptic is touching, feeling. Okay, so what do we do with our building blocks? We are building the picture of what we want. The object is hard. Okay, so it's not visual picture, the person is blind, but the object is hard to, when you touch it, it is solid, it is like, not like water, it is like stone, like concrete, hard, and the places that are empty are soft, like water. Think about it like a microwave, okay, like you make your food warm in the microwave, which heats the food from the inside out, but by vibrating the molecules with resonance. I'm not getting into how it works. It's like everything that contains water, it vibrates the molecules and then it's hot. And where there is a lot, like in the center, it's more hot. So like it's like from the inside out. Okay, so we start with the innermost, inside most point in the object, and we vibrate it with our focused waves. Then it gets hard, and the hand can sense that it is solid. Okay, like the blind man is touching the liquid, the custard, and suddenly he's in an area where it is like rock, like hard. You cannot pass his hand through this. Then we build the outer shells of the object. It's almost like 3D printing, but much more real time. Like 3D printing takes a lot of time. This is like almost immediate because we build it very fast from all directions at once. And it does not need to solidify over time. It's instantaneous. You hit the liquid with an impact and it hardens. Okay, it's exactly like you jump to the pool and immediately, if it's from like high, like if you fall from the 10th floor, immediately the water is like rock, like solid concrete. Okay, so it doesn't take time like 3D printing. non-Newtonian liquid calculates like immediately. Okay, so in this way we can shape with the help of the computer. Each engine is controlled by a computer, and there are engines like all around, many engines and pedals controlled by a computer. So in this way we can shape with the help of the computer the solid 3D shapes that the user will feel in every moment. Like we say, here will be hard, here will be hard, here will be hard, and everywhere will be soft, for example. So we have like triangle. So the solid 3D shapes that the user will feel in every moment. And of course, like if we have like a deeper pool, like 1 meter on 1 meter, like a sphere, then we can put waves from all directions, from below, from above, and like have 3D shapes, not just 2D shapes, not just a circle, for example. We can have a sphere. Okay. Okay, so in this way we can shape with the help of the computer the solid 3D shapes that the user will feel in every moment. Of course, the refresh rate is not immediate. It's not like we can reset the liquid to soft and start again many times each second, but it's much quicker than printing 3D printer models. This is like as if 3D printed models can only make frozen still videos, and this is a slow motion video. Okay, like a few, like 1 frame every second, but it's video, it's not like only 1 photo. Of course, we can also like break the Newtonian fluid if we know how, with the like necessary waves, small waves. Like confuse it again so it's not hard. The user can feel complex 3D shapes that are created dynamically, and similar to the previous part of the invention, this is part 2, but similar to the part 1 of the invention, we can respond to movement in different dimensions, etc. Okay, like if the user moves his hand to here, maybe like this means that he zoom, and like now he sees like some close-up of the shape or something. Like we can make some changes. It's like animation. It's not like album of photos, still photos frozen. It's like alive, because we are creating each frame with the computer, pushing from all sides, creating new image, creating another image, and so on. Of course, we cannot give the user the sound equivalent of being inside this liquid and hearing through the liquid, because the liquid is viscous. We do not want the user to wear goggles and dive into it. He might drown and die. You cannot swim in such a thing. When you move, it hardens. But we can give him the impression of what his hands hear, like inside the liquid, with headphones. Okay, we put headphones, and he listens while his hands are playing in the water, in the liquid, not water, custom. The computer calculates to which direction his hands are pointing. For example, in parentheses, we can set up the control interface in any way desired, close parentheses, and the user hears in his headphones the proper soundscape. Here, scrubbing rapidly will not work because the hand will get stuck. Okay, if you move quickly, it becomes like stone. The user needs to comb the water with his hands very slowly, and then the hand can pass. This is similar to how in Dune, okay, the novel or the movie Dune, make yourself a favor, watch the one from 1984. Anyway, not the new one. The old one is a masterpiece, the new one is. This is similar to how in Dune, the personal shield defends against fast-moving bullets, but a slow-moving knife can penetrate it. The slow blade penetrates the shield. It's a sentence from the quote from the movie. Okay, I hope you liked the inventions. Thank you so much. Thank you so much. Bye bye.